Yeah. So Pinaki
Yes, sir, I'm doing.
Pinaki is online.
Is it
No.
okay?
Yeah.
Yeah, it's okay.
Okay, good.
Just I just
Yeah,
checked.
no, just because sometimes you check the day before and everything works, and then 2 minutes before nothing works. So,
Yes.
so you never know.
Can you make it just a big slide because, or is it coming like that? This next slide, or I don't know. I mean, it is also fine. We can look properly.
Why? Because you see this one.
Yeah, I also see the next one.
Okay. Sorry. I think I understand where is the problem. Let me see.
The Professor Pinaki Majumdar is here. So let me introduce you to each other. This is Professor Rosario Fazio from ICTP, and this is Professor Pinaki Majumdar.
Hi,
Hello.
nice to meet you.
Nice to meet you.
Sorry, I'm trying to, of course. Okay, I did not get this.
Okay. You just, if you play, is it, it's a Mac, right?
Now you see nothing?
Yeah, we see
Now,
that.
black.
Okay, so let's do the following. Sorry, no, sorry. Okay, I think I have a symbol way. Now it should work.
Yes.
Yeah, it's perfect.
Okay, sorry. I was trying to be sophisticated with 2 screens, but then I project on the wrong one. So now it's I just go for the symbol version of it. Okay.
Okay, so let me request Professor Pinaki Majumdar to chair the session.
Yeah. So welcome to Professor Fazio, who has been to HRI, I believe. Ujjwal told me at some point.
Yes.
And we would love to have him back once we are past the COVID phase. So he'll talk about quantum time crystals. And if I understand right, the protocol is we don't ask questions during the talk itself. We keep questions for the end. They show up at the chat box, and then they're passed on to the speaker for response at the very end. Is that right, Ujjwal?
Yes.
Okay. So without further ado, Professor Fazio, we go ahead with the talk.
Okay. So first of all, thank you very much for the invitation. I'm really glad. I mean, I would have been much happier to be in person, but I mean, we have to cope with the situation. So thanks a lot for having invited me and to give this talk. So I will tell you a little bit about quantum time crystal. So I will try at least my best to give a long introduction. So I don't know if I managed to tell you all the things I prepared, but at some point when time is over, I will stop. So I really would like to start with something which is, I mean, you know very well, and it's been discussed for many years, and now it's reality. It's about quantum simulators. Now, quantum simulator is a quantum system which we are able to control, and the original idea and why simulators were called simulators is that because it's a way, it's an efficient way, in the words of Feynman, in which we are able to describe, to analyze, and study a quantum system because of complexity of quantum of the Hilbert space. Then a possibility to simulate the physics of given model Hamiltonian may be much more much simplified, but just using as an auxiliary method instead of numerics or analytics, but just other quantum system, but just drive their evolution in a controlled way. Now, what I'm going to tell you today is a different use of quantum simulators. Actually, not only you can simulate what I mean, let me say, reality. Actually, there is also another very interesting aspect of it, that quantum simulators in general may also allow you to address questions then cannot be really addressed in real system, because it's very hard to disentangle all possible parasitic effects. So I don't know, one example is, for instance, thermalization. I mean, fundamental issues like how closed system thermalize, it's very hard to study in in nature, because there are so many effects which will hide the true properties of unitary evolution, but you can do it with the synthetic system. Another aspect which will be central in my presentation is that they also allow you to realize new state of matters. In particular, they will allow you to realize probably phenomena that in reality are very hard, if not impossible, but then you can really engineer your quantum system in the lab in such a way that some phenomena which are allowed by the laws of nature can indeed be observed experimentally. And time crystals is one of those examples. So far, the only observation, let me say that for sure the best and most clear observation of time crystals come from systems which are also simulators. So I'm going to tell you a little bit also about the experimental realization, and this was possible only thanks to quantum simulation. So I just close this small interludio and go back to the heart of the presentation. I mean, what I'm going to say is very trivial. I mean, we know that I mean, in nature there is a plethora of example in which a system, I mean, complex system ordered by condensing to a superconducting state, or just by aligning spin in order to have a ferromagnetic behavior. And this this ordering takes place through, I mean, when the system crosses a phase transition, and this phase transition may be induced by thermal fluctuations, or below a certain temperature, then system goes from a paramagnetic to a ferromagnetic, but also can be of quantum nature, induced by quantum fluctuations. And so below so in the ordered phase, the ordering is described by some parameter. I mean, I'm not going in any details about, I'm talking about standard phase transition where a local ordered parameter is enough. But say inside the phase, then there is some ordering. For a ferromagnet, this is a magnetization, just local magnetization. And what is important is that the magnetization just corresponds to the fact that the state of the system breaks spontaneously some symmetry of the Hamiltonian. So for a ferromagnetic, it's just, for instance, rotational symmetry. Now, this classification, which goes back to Landau, has been exploited in a huge range of phenomena, from low energy to high energy, and all possible, from the simplest to all most sophisticated symmetry, spontaneous symmetry breaking has been described. Now, in all this huge list of cases, till this paper of Wilczek, which for the first time arose this question. Now, time translational invariance was never considered, or more specifically, people did not have any evidence that time translation invariance could be spontaneously broken. Now, the first to address this question, if this is indeed possible, was Wilczek, and an analogy with the case in which space translational invariance is broken, which leads to just crystalline, I mean, ordinary crystalline phase. Just name this hypothetical new phase, hypothetical at that time, but of course I'm going to tell you that this is indeed has been realized. It just names time crystal. So he just, I mean, in his paper, he just asked the question: if time translational invariance or spontaneous breaking of time and translational invariance is broken, and if it's broken, then the system should enter in this new weird phase, which he called time crystal, and this is the name that is currently used in the community. You will see that the analogy is not that strict, and actually there are some very important differences compared to ordinary crystal. So, trying to make some historical review of the topic. At the beginning, especially, people ask if time crystalline phase could indeed be allowed by the laws of nature. Now this question is understood, but at the beginning was not just evident or clear why time translational symmetry breaking was never observed because people did not look in the right place, because it was impossible to realize the correct condition, or just simply because there was no this was not allowed by the laws of nature. So the first question was now has a positive answer, but the next question that people try to address is that if such a phase can exist, how is it possible to characterize? Okay, and so this question led to some initial controversy, but I think the situation now is pretty clear. And connecting to what I said just at the beginning of my presentation, so if a time crystal can exist, and we know that it can exist, where to look for it? I mean, you would see that it's not that trivial to observe it, and probably this is why I mean I'm sorry. And this was, sorry, I have some small problem with the screen. Okay, so, and this is why people did not really have a chance to observe it before a few years ago. Now, these were the initial question. Now there is a positive answer to all of this, and in the second part of my presentation, I will try to make connection to other phenomena. So just trying to understand if this is a completely new effect, or there is something that we already know about it. And if I have time, but I'm pretty sure I will not have time, if let me say, if there is if there are cases in which this weird state of matter may be of some use for something. Of course, I mean, so, and I will try to argue, if I have time, to say that, that there are cases where a time crystalline phase can be used in some quantum protocols, but this I would like just leave it for the last part. So initially, but I have no time to go into the details of the discussion. There was really a very vivid debate motivated by the papers by Wilczek. Especially there were contributions by Bruno, Nozière, Volovic, Sasha gave very nice contribution, because at the beginning this idea of Wilczek was not completely defined, and it was not very well understood how to define a time crystal. Now, this is the outline of my talk, so I will spend some time in introducing time crystals. So I will restate the problem, try to give some definition, and I will tell you essentially few key steps in the development of what is understood about nowadays about time crystal. Of course, due to lack of time, I mean, there's a finite time of this presentation. I will, I mean, I can only just sketch some main aspect of it. I will tell you a little bit about, so I will first, in the first part, I will concentrate on Fouquet time crystals, what is known about Fouquet time crystal, which I will define in a moment. While in the second part, I hope to have time for it, I will introduce a different way to realize time crystal, which does not rely on unitary evolution, but should occur in many body open system. And this last say form of time crystalline phase, I will try to make connection to phenomena that we know much better, which is essentially synchronization. And I will try to make some connection. I mean, there's nothing rigorous in what I'm going to say, but I'm trying to make connection between synchronization in quantum system and time crystals. Okay, so I will start with, I'm sorry, but since I had to eliminate the second screen, I have less control of my slides, so I apologize for that. So these were essentially the main points I wanted to list. So before I start, let me just acknowledge the people. This is a topic which I like a lot. I've been working with several people that are listed here, but as I said in the first part, I will spend most of the time on introduction, while in the second part, I will mostly concentrate on these few papers here. Okay, so let me start with the definition of time crystal, which came few years after the first paper in 2012 by Wilczek. So let's consider some local order parameter, phi, which depends on space and time. I mean, you will see the definition is pretty natural, but somehow, I mean, it took some time before just focusing on the essential features of the phenomenon. Now, this local order parameter may be in a ferromagnetism, may be the local magnetization. Okay, so in a standard long-range order, so what you do is just to look for the correlators. So the correlation in different space. So just take the same time, but different points, x and x prime. Take the limit in which the volume, so you take the thermodynamic limit and then look at the behavior of the correlators as a function of space. Now, in a ferromagnet, this correlator will go to a finite value, which is essentially the square of the magnetization. Okay, so Watanabe and Oshikawa actually very naturally generalize the equation, so the definition to some time crystal, saying that if time translational invariance is broken, then this correlator will not only depend on the space, but it will also depend on times. Okay, and time ordering essentially will appear if, when you take this limit x and x prime going to infinity, the correlator does not approach a constant, but will have some periodic function. So here is not really crucial that it is depending on the difference between times. It just depends on two times. Okay, and this is essentially, in a very visual term, you should imagine that it's a kind of synchronized motion of the magnetization. Okay, so which has some non-trivial dynamics, which is correlated at arbitrary space point and times. So if you assume that this is a good definition, of course there are cases which are not included in this definition, but I would not discuss much about those. What was very interesting and important was that Watanabe and Oshikawa just proved that under general assumption, they just proved that if you assume that this is a good definition of time translational symmetry breaking, then a system in its ground state or in thermal equilibrium cannot have any time crystalline behavior. Actually, they proved that this function is bounded by, so the oscillation of this function is bounded by a function which goes to 0 when the volume goes to infinity. So this means in the ground state or in equilibrium, there is no oscillation in the correlators between order parameters in different points in space-time. So this was a very important result because of two reasons. So the first reason is that it just tells you that that in equilibrium, essentially, there is no hope to observe time crystalline behavior. But it leaves open the possibility to have time crystals out of equilibrium. And this is very important. Sorry, I just go back 1 sec. And this is very important because if time crystal exists, then the analogy between space crystals and time crystal does not hold. It's just our imagination, because you see, space crystals are equilibrium phenomena, while time crystalline behavior, if there, can only be there outside equilibrium. So starting from this no-go theorem, people started to study possible cases in which time crystal could be observed. Of course, you may imagine that moving away from equilibrium just gives zillions of possibilities. The first example, very successful, that was considered by 2 theory papers by Else et al. And Kemani et al. In 2016, was the case in which quantum system, many body quantum system, I will talk, sorry, I forgot to say, I will, for most of my talk, I will just mention quantum system. Actually, there's much more about quantum time crystal rather than classical time crystal. They consider a specific yet very, very interesting way to just drive a system out of equilibrium. That is the case in which the Hamiltonian is driven periodically. So the system evolves unitarily with an Hamiltonian which has a period capital T. Now, for this periodically driven system, essentially, I will not be of any rigor, but essentially the idea is that if the period of the Hamiltonian is capital T, spontaneous breaking leads essentially to the situation in which the observables will have a multiple of the period. Now, if just in this form, that there is some triviality that should be taken away, and I will try to explain. But the idea is essentially that a Floquet times crystal is a phenomenon that, in other terms, is like period doubling. But this period doubling has some key features which are very important. So first of all, it's spontaneously. So it's a spontaneous breaking phenomenon, which means that any finite system should not show any period doubling, but this should emerge only in the thermodynamic limit and should be an effect of the many body behavior of the whole system. So in less sophisticated terms, you may say that a Floquet time crystal is a kind of many body period doubling phenomenon. Now, if you go into those papers, then there is a more rigorous way to define a time crystal just by looking at the Floquet eigenvalues and the structure of the Floquet eigenvalues. I will try to be just a bit sloppy, and I just try to give you some hints on what happens. So actually, in this paper by Elze and co-workers, they proved that if time translation asymmetry breaking occurs, then any Floquet state violates clustered properties. So the idea is very similar to the, for instance, if you take an Ising ferromagnet, then if you take a finite system, this will be a cut state. It will be up, 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 plus, minus, whatever, down, down, down. Now, if you see that this system does not break the symmetry, the Z2 symmetry, however, it violates cluster property. The same structure of that in a quantum system, for instance, is found in the eigenstate of the Hamiltonian should be reflected here in the Floquet state. Okay. Just without going in any details, let me tell you that this many body period doubling should appear. So there are certain requirements which are contained in this definition. So for instance, another property which is very important is that the Floquet eigenvalues should have a doublet structure, which reflects the fact that you will develop this period doubling. But something which is very important is that this period doubling should not be related to any fine-tuned Hamiltonian parameter. So I will make a very simple example in which you will get the feeling. I mean, I can construct very fictitious situation in which I may get some period doubling, but this has nothing to do with many body physics or thermodynamic limit, and then you will see that in those cases, this period doubling is bound to be destroyed by any epsilon perturbation. So it should be robust. And as I said before, a very important thing is that this oscillation, this anomalous oscillation should appear only in the thermodynamic limit. Okay, so otherwise, this is not the case. I mean, this is not a good definition, a good situation. So let me give you one example. Sorry, I'm going very slow, but I thought this might be much more useful rather than giving my presentation of my results. So let me give you one very simple example in which you start getting the flavor of this time crystal. Just consider a specific periodic Hamiltonian in which for a certain time, then you have just an Hamiltonian, which is Ising with ZZ coupling. For the moment, just ignore disorder, okay? You will see that disorder will end in a sec. Then you do a pi pulse, so you flip all the spins. Then you just evolve with the free Hamiltonian, pi pulse, and you continue this way, okay? This is a very simple example. And let me start with very specific states. I mean, this is the evolution. It's very simple. Now, if you consider this is the period, okay? The period is just given by a free evolution plus a flipping. And then I would like to measure the magnetization. And it's easy to see that the magnetization doubles the periods. Because, for instance, you see that if you start with a given state, I'm starting with a specific state. Then after a period, then all the magnetization is, all the spins are flipped, and I need 2 periods to flip it back. However, this is not, I mean, we all agree that this has nothing to do with any spontaneous symmetry breaking, because this occurs only for few spin. And indeed, if you just take this example and you start putting not a perfect pi pi pulse, but just the form, the flip pulse is not perfect, or you just take free evolution without interaction, then it's immediate to realize that this periodic flipping of the magnetization is completely fragile. It will disappear. So period doubling will disappear because of any perturbation. In addition, if you have a generic evolution Hamiltonian, then what happens is the system, since you are driving the system just gets increase its energy. So locally, it may, in generic terms, I mean, under generic condition, may approach a system with very high effective local temperature. So, I mean, you expect that if you are at the system which, I mean, thermalized to infinite temperature, then the local expectation values will be completely structureless. This means that you have to find cases in which driven system do not heat up. Okay, so in a sense, this tells you that in a driven system, a time crystal may exist only under special situation in which, let's say, ergodicity for some reason is lost. One cases that people studied in great details is the case in which ergodicity is lost, is that of many body localization. That's why here I indicated interaction and disorder, and this is indeed the case which was first studied in 2016 by Else et al. They did exactly what I told you in words, and if you see just in the lower graph on the right, then this Z of t just measure the time, so essentially the period doubling correlation. So this Z, if there is a perfect period doubling, the Z will be 1. Now you see that here there are 3 curves. And actually you can do similar, I mean, you can do a simulation with no disorder and you will see that the system does not show any finite order parameter. But if you include disorder, so the system does not heat up, then they did some exact diagonalization. So these are the 3 curves, and then you see that eventually, since it's a finite system, this Z, which is the parameter that tells you that the system has this time crystalline phase, will eventually go to 0, but it goes to 0 with a typical time which increased with the system size. And actually, if you just go in some details, you see that it increased exponentially in the system size, telling you that this oscillation will persist in the thermodynamic limit forever. This experiment was performed. These are the experimental results. It was performed in 2 groups, in the groups of Monroe and the groups of Lukin, that essentially did what I described you in the theory paper in 2016, and 1 or 2 days, I think the papers were published in 2 years later, they observed exactly this behavior. Now, I told you one example in which a time crystalline phase or a Floquet time crystal was possible only because of disorder. Now, is it possible to observe it in the absence of disorder? I mean, is disorder crucial or not? Actually, this is not the case, because as I tried to convince you, then what is really important is the fact that ergodicity is lost. So if there are other ways in which this happens, this could be the case. Now, there are several examples which we studied in various forms. The simplest probably examples in which in which this occurs is what is called the LMG model, Lichtmin-Meshkov-Glick model. This is a very simple example, so with a long history. It's just a quantum system of spin 1/2 interacting through an infinite range Hamiltonian. So there is an infinite range Hamiltonian plus a transfer field. Now this Hamiltonian, I mean, it's exactly solvable. It's very easy to study, and it has a spectrum which has a very interesting structure. It shows that essentially there is a whole part of the spectrum up to a given symmetry edge in which the eigenstate breaks the Z2 symmetry. This is the key, and this is not this is an integrable system, so does not locally thermalize, if you wish. So here essentially is the structure of the Hamiltonian and not the presence of disorder, which has so many constraints due to the integrability, which for other reason makes a quantum crystal possible. I don't want to waste too much time on this because of lack of time. I mean, if I manage, I really would like to spend the last 10 minutes on the last part. But just to show you, if you compute the magnetization, you just see the double period doubling exactly as in the case with the oscillation. And the gap between two Floquet states, which essentially is related to the decay time of this oscillation, will increase in time exponentially. So this is possible even to show that the thermodynamic limit actually will correspond to kind of classical limit, and then calculations can be done even analytically. So disorder is not important. There are other examples in which ergodicity breaking may lead to a time crystalline phase. So due to the time, I will skip this part, and I would like to jump to the second part that I really would like to address, because I'll be essentially because I like it. Okay, so this is so first of all, the Floquet time crystal, break a discrete symmetry. So the idea is that you have a periodic evolution, and then it's like charge density wave in a solid. You have a periodic potential, and you just get some periodicity which is double with respect to the potential. But first, you may ask if it's possible to observe, so what is the effect of an environment? And sometimes it destroys, sometimes may not destroy. And the other question, you really would like to know if it's possible to have a continuous time crystal. So this leads to trying to understand if it's possible to have time crystalline behavior in a dissipative many body open system. And this is a topic which was analyzed in several papers. I mean, here I list some of them. And again, so this phenomenon is somewhat related to something which we know already, which is the fact that in a dissipative system, you may have limit cycle in the steady state. Now here a time crystal is something which is a kind of, a limit cycle which appear in the thermodynamic example. So you see that in this case, if you start with the open system and you look for time crystals which do not necessarily have the same behavior as before, then I mean, actually the coupling to a bath is not only not detrimental, but actually is the key to realize a time crystal. So let me say a few things. So the no-go theorem that I told you before does not apply because, I mean, essentially we are entering a steady state, which is a non-equilibrium state. Here there are no experimental realization at present, but hopefully there might be something. Let me say right now that this limit cycle can be interpreted, and I just make this point because I think it may be interesting to make connection to phenomena which we know better, to the fact that you observe that the system gets into a kind of synchronized dynamics. So you just may imagine that you have this many body open system which enters some phase, which is, for instance, characterized by some local magnetization. This magnetization will enter a limit cycle which is of a many body nature. This, you see that if this happens, then in the steady state the Lindbladian, or the equation which govern this, is translational invariant, but the steady state itself, even if the Lindbladian is translational invariant, violates this. So that when this may be the case, there are papers that analyze this. I especially mentioned there's a paper by Anna Samper and co-workers, and papers by Albert that give general properties of when this may happen. I just want to conclude with a very simple toy model, which just illustrates what I meant. It's just very, very simple, but it has the merit that can be solved. Just take 3 spins that are coupled in a collective way to some environment. So the coupling, capital S, is the total spin. Okay, so this dynamics has been studied in several for many years, and actually very recently there was a paper finding a transition between 2 different phases with the SZ equal to 0 and different from 0. But if you go into some details, and which is somewhat we pointed out, these 2 phases have very interesting different properties of the Lindbladian. So when omega 0 over kappa is larger than 1, then somewhat you have a gap in the Lindbladian. In the other case, the Lindbladian is gapless. Now, as a result, what happens is that if you look at in the case in which the Lindbladian is gapless, so you have many eigenvalues which coalesce to 0 in the thermodynamic limit, then you see that if you look at the average value of SZ, you will see that there are oscillations, and these oscillations slow down when n, so n is the number of spin, becomes larger and larger, and actually they persist forever in the thermodynamic limit. So I think I would like to leave some time for discussion. So I really would like to skip this. The only thing I really would like to tell you is that so yes, I really would like to tell you. So first, 2 things. I mean, and with this I will conclude. So first of all, that maybe there are these exotic phases in many body open system may have systems where to study it. I mean, there are no experiments, but in principle, if you take optomechanical arrays or cavity arrays, coupled cavity arrays, or BC in cavities, all these are interesting systems where this phase, this limit size, many body limit cycle or time crystals may be found. So far, there are several works. Most of them, however, are mean field-like. And it should be said that mean field is not that controlled, so that you are sure that what you are predicting is close to reality. So unfortunately, I mean, this is very hard to simulate with accurate, with great precisions, and still there is some work to be done for that. But I think there are possibilities in this direction. There is one last connection that I would like to make, is that if you see this synchronization, this time crystal in open system, it's another way of saying that the system synchronized. Okay, so you have an order parameter which oscillates in time. If you think to classical example like Kuramoto model, so this somewhat resembles similar type of thing. So you have dynamics which is synchronized. So there may be some connection between time crystal in open system and synchronization, and also to what people call finite frequency criticality. So essentially, at criticality, the mode which becomes soft is not the omega equals 0, but finite omega. So with that, because of time, I will conclude. What I did was just to review a little bit the physics of time crystal in unitary driven systems and in many body open cases. And in this last, I try to make some connection to other phenomena like synchronization. So and with that, I thank you for the attention. Thank you very much.
Thank you very much. Now, Ujjwal, should I pass on the questions one by one to Professor Fazio?
Hello. Yeah. So there are like two ways. You can either read him the questions, or maybe he can read it directly from the chat box.
Read it directly. It's marked to everyone, I thought. So maybe in his chat box, he can take a look. Professor Fazio, can you see the questions?
Sorry, I have to stop sharing the screen.
Okay,
then.
stop sharing the, yeah.
Okay, yes. Yeah, now? Then I see the question, yes.
Yeah, so maybe you can just answer them yourselves.
Okay, so I don't need to read it because everybody reads, right? Okay, so the first question is about the magnetization. Now, what the question is about the initial state. Now, in order to have a robust time crystal, the states, the result should be independent of the initial state, except for possible singular situation. Actually, this is a key point. If you have cases in which the dynamics is depending on the initial state, this might be just most probably just a pathological example. Now, if you put disorder in the magnetic field, yes, this is also as long as many body in the MBL phase, and you may have MBL phase because several reasons, and if you are in the MBL phase, this is fine. Then is another question is how time crystal behave in the grand canonical ensemble. Now I'm thinking, because I think so you may have a time crystal in which, for instance, you break U1 symmetry. So let me say, so far time crystal, in time crystal, time translational symmetry break, it's very nice this way, you see, because if you say something, then you can, people don't tell you that you did not give the right answers, right? So it's good, no? Now, in time crystals, so far people understood that you have the time translational symmetry breaking is always accompanied by another type of symmetry breaking, like rotational, whatever. So you have a macroscopic magnetization which breaks also time translational invariance. So I think the definition is the same, and actually the no-go theorem by Oshikawa and Watanabe was derived also for the grand canonical case. Now, then there is a question, so I read it, it's somewhat strange that equilibrium do not support time crystal steady state do. Yes, it is strange. However, the key is that equilibrium states are spatial. So let me say it this way: are spatial steady state in which the Hamiltonian is diagonal on the Hamiltonian basis, which is also, related to the evolution operator. So, and I think this is the key. While a generic steady state does not need to be, actually it's not an equilibrium state in general, and there what happened is, so you may have several situations. It's not only a single steady state stable is the possible solution. It's like nonlinear system, okay? And this is the key. Now, the question is about only period doubling, and this is the part I skipped. Actually, if you may construct locked models in which you have multiple periods. So there are certain rules to construct this, but there are cases in which you may have tripling, quadrupling, and so on and so forth.
We ask questions vocally as well.
Yes.
Can we directly ask the questions as well? Chairperson.
Yeah, you already have a list of questions here, so let's finish with them and then you can ask questions.
Sure, sir.
Okay, so I just finished. I think that I have the last two. So what is the reason in the toy model ergodicity went to zero and lead to time crystalline behavior? So there, frankly speaking, I don't have a good intuition for that. So the key is that the Lindbladian is gapless. So you have the fact that it's not a steady state, but you get a steady subspace. Okay, and then you may have a limit cycle within this subspace. This was the. Now, can TC be said to be in a prethermal state? Well, that's a good point that I did not mention. There are cases in which actually you may have prethermal phase which lasts for a long time. So you may have cases like long-range interaction in which, in this prethermal situation, you may have flow-K time crystal, but then eventually, after an exponentially long time, they will die out. Now, and the last question is that since there are possibility of periods other than 2, is there a chance that the system goes to chaotic behavior? Yes, there is a chance. So So this was not very detailed study. So we did a case study for actually for a classical spin system, but for quantum, I don't, yeah. So it goes to so people realize that when you have a transition between time crystal, you go to some thermal effective thermalized situation, and the order parameter vanish. Yes, for infinite system, correct. I think I think I answered the question in the chat. So if there are other questions, I'm ready.
Ask questions now.
There are some questions you missed.
Oh, sorry.
A bit, because it's coming one by one. So, so I think you there is a Himadri, I think, wrote very nice questions. Where
Is there any direct analogy between time crystal and many body localization? This one.
Yeah.
Okay, sorry, I missed this. So it's not an analogy. Now, let me say the following. So if you take the paper by Kemani et al., actually they don't call it time crystal, they flocate time crystal, they call it like pi spin glasses. Okay, so in a sense, there are disordered. Sorry? Okay, so there are situations in which the glass phase, in a sense, also break time translational in the time translation invariance. In the example I presented, MBL was an instrument or just a requirement not to make the system heat up. Okay. So you may have situation in which you have MBL without time crystal or MBL and time crystals. Okay. So it's not a one-to-one correspondence.
And then there's a second last question. Can you go to the last but one?
Entanglement, yes. May help. So entanglement may help a system to reach equilibrium. Again, time crystal behavior cannot be demonstrated in equilibrium. So entanglement is not good for such behavior. So entanglement, I don't think, yes. So it's not that it's good or not good. I mean, it's difficult. I think that, so for instance, if you take LMG model, entanglement still grows as a volume law, but not the infinite temperature, because in the gravity and there is time crystal. In the MBL, it grows like log, and there is time crystal. So my first answer is that entanglement may not be the key element, but I should admit, if I'm not mistaken, there are not works that they study really how entanglement behaves in a time crystal. I don't think there are, I may be wrong, but I think there are no detailed studies of the role of entanglement for a time crystal formation. But the examples that were shown, yeah, entanglement was not the key. So I agree with the statement. Did I miss?
No, I think you answered all the questions. And so maybe now we ask if anyone else has any question.
Hi. Hello, am I audible?
Yes.
Okay, so this is a follow-up on the question I asked about whether there can be more than period 2 oscillations. So this depending, right now we saw that kind of pi pulse is robust. Would you say that this time crystal makes pi pulse robust, right? Even if we introduce error in the pi pulse, it's still, the system still sees pi pulse. All right. Mm-hmm. So now is it possible to do the same for say pi by 2 pulse? Now, will this depend upon the coupling that this is like you used Ising coupling, IZ? Will the form of the coupling have an effect on what kind of robustness we see in what kind of pulses?
Yes. Now, if you take a generic, so you see that, just imagine that the simplest, I think, example in which instead of having up down, you have a clock model. Okay, it's just on the clock you have 3, 4, n variables. Okay, and then instead of pi pulse, you can just do kind of phase shift of 1, 2, up to n for n clock, right? Now there is a whole classification in which, depending on the shift and the eigenstate of the pure Hamiltonian or some properties of the bare Hamiltonian, then you can say if the Floquet time crystal is robust or not to this order.
I see. So for every angle, I can find an interaction. Technically speaking, I can find an interaction for which I can make that particular angle robust.
Yes. Yes.
I see. Thank you. Another thing maybe about the same thing about MPL. So all the time crystals need to have many-body localization in them, right? Otherwise, they'll heat up again.
Yes, but not. I mean, you may have a situation in which there is no. I mean, it's a good. It's the best. A very good situation. MBL, it's perfect. Yes.
I see. Thank you.
Yeah. Can I ask a quick question? So this is following up on Ujjal's question about steady states. So if I understand you right, periodically driven systems can exhibit time crystal end behavior. That was the Floquet example. Are you also suggesting that if something is steadily driven without explicit time dependence, I can still end up with a state which is time crystalline?
Yeah, because essentially, so let's say the essence of symmetry breaking is that you have a dynamics which is time translational invariance.
Right.
But the state which is related to this dynamics breaks the time translation.
Exactly. And what would be a simple example of that?
So if you take a Lindbladian with the time-independent coefficients and time-dependent Hamiltonian,
okay,
this is translational invariant. I mean, it does not depend on time, but the steady state is maybe a cycle. So the steady state.
Okay. And these are known in nature. There are examples people have discovered where this thing actually happens.
No. So let me say the following: the fact that so you see, here there is a debate. So I'm not able to give you a very good, precise answer, because many people would say that the fact that you have limit cycle in nonlinear system, this has been known for decades.
Right.
Now here I would say the key is that it's many body effect. So this limit cycle should emerge only in the thermodynamic limit.
Mm-hmm.
Now, but there is another question. You may say, and actually here the discussion becomes a bit difficult, is that you may say, okay, if I take a dissipative system that actually, nonlinear dissipative system which show a limit cycle, after all, if I purify this, I mean, I just increase the Hilbert space to take into account also the environment, this actually, it's really an open, a closed system in the thermodynamic limit. You see, I mean, the question is that a dissipative system, if you just write as an Hamiltonian system, it looks like a big closed system in the thermodynamic limit. And so here, I have no good answer. So I'm thinking, but I don't have a definite answer. For sure, there is a connection, but I don't know if it's truly new phenomenon or is somewhat related, because limit cycle have been known. So.
Yeah, but this would be a better example, because in the Floquet case, you're actually driving the system. You're breaking translation symmetry by hand. And as a response to that,
well, but there you break it discretely. So it's like, you know, you have spin density wave. So you have a periodicity Hamiltonian, but the state doubles the periodicity, like in a spin or helical state or something. This is the same as flow K.
Okay, other questions?
I have a question.
Chat box, maybe? I mean,
no, I think one should avoid the chaos. Otherwise, so it's not quantization of time. So it's so there's nothing. I mean, times is classical. So it's just you observe. It's the property of the system, not of the time.
I have a question.
Go ahead.
How does one reach the infinite thermodynamic limit when we are doing Lindblad dynamics?
Oh, you have to take the number of spin to infinity. So this is what the example I gave is just a lattice spin 1/2, and then you take the limit of the number of spin to infinity.
So this one can do when the Lindblad equation is exactly solvable.
Yes. Otherwise, yes.
Yeah.
So this is why we consider that case, because you have I mean,
the specific case of your LMZ model or the toy model that you have shown.
Exactly. Yes.
Yeah.
This is the case. These are symbol models where you can really push to the limit. Yeah.
Thanks so much.
Okay. So, Jal?
Yeah, so we thank the speaker now. And we are every day having, with the permission of the chair and the speaker, we every day are having a photograph at the end. So everybody, we request, with the permission of everybody, we request everybody to put on their videos. And Ganesh, you would take it, the picture?
Yes. Yes.
So you would say, tell us to say cheese, no?
Yeah, I mean, I'm waiting for people to turn on the videos.
But do you manage in one picture to take all?
No,
I'll take a couple of them.
Okay.
Yeah.
So we have to keep smiling.
You have to keep.
All right. 3, 2, 1, cheese. Say it again. Cheese. All right. Thank you.
Okay. Thanks a lot. I hope to see you soon in person.
Thank you, Saru. Thank you, Pinaki, for chairing, and thank you, Saru, for the talk.
Thanks a lot. Ciao. Bye-bye.
Bye.
Ciao.
Chandan, you can put off the YouTube.
Yes, sir. Sure.
And you can leave. You can make any one of us as the host, and you can leave, because
Okay.
you are the only one who is not at home.
Thank you. Okay. Thank you, sir.
But still there is live streaming. So